Alright, so picking up where we left off from part 1 of 10.3. Part 2, we're going to get into standard deviation and normal distribution. So first of all, what is standard deviation? So there is a formula for this, and there's a good chance you've already had to do this. I know my daughter's just took Algebra 1, and she had to do this formula for standard deviation. So good chance you've already seen this. Good news is we're really not going to be working with the formula on this one. We're really going to be doing all these calculations with technology. So I do want to mention, though, a couple things. First of all, what is standard deviation? Standard deviation has to do with how spread out the data is. Okay, and so I know that if I am, certain items are within one standard deviation from the mean, right? We're talking about the group that is closest to the average within your data, right? And the more standard deviations you use, the farther away from the center you are. If something has a really high standard deviation, that means your data is very spread out. If it has a low standard deviation, that means your data is very close together and it's not very spread out. So for example, let's just say this class averaged an 80% on a test, right? And let's just say all the tests were really close to 80. They were somewhere between 75 and 85, right? That would have a very small standard deviation. But if a different class still had an average of 80, but the numbers were super spread out, they were everything from let's say 50s to hundreds, right? Way more spread out, but they still had an average of 80. They would just have a much bigger standard deviation. So you can have two sets of data with the same mean, the same average, but very different standard deviations depending on how spread out the data is. The symbol that we're typically going to see is this guy. This is the formula for when we have what we call the population standard deviation. That would mean you actually calculated the data from an entire population, right? So if I wanted to know how many of our students are going to attend the next football game at our school, and I literally surveyed every single student in the school, that would be a population. But if I also wanted to know how many students are going to the next football game, but I didn't have a chance to survey every student in the school, and I just checked with my class, and my class, I found out that, I don't know, 20% of my kids are going to go. So I just assume 20% of the whole school is going to go. All right, that's what you call a sample, right? That would be a sample of the data if I only surveyed a group within the population. So this little symbol, which is the lowercase symbol for sigma, that's this guy, the lowercase version of this in Greek, that represents the population. Okay, and this is the formula for the population. If you were to actually do a sample, right, instead of the population, this changes to an S, and this changes to n minus 1. Right, it's like their way of adjusting for the sample rather than you surveying the entire population, which would be way more accurate. So let me just show you how we can do this in our graphing calculator. And in the graphing calculator, it's like no different than what we've already been doing. Hold on, let me increase the light in here so you can see my calculator better. So when we calculated our list of data in the previous lesson, remember we saw the mean up there. And I did point out the standard deviation. So the S of X would be your sample. This one right below it would be your population. Right? So there's the population. And then what we were looking at in the last lesson were those 5-number summary values. So it's all on the same screen, which is really nice. So if you're using the graphing calculator. If you are not, and you're going to put a list into Desmos, let's take a quick look at that. Get rid of these guys. And then instead of a box plot. By the way, guys, I type in the word box plot or I type in the word stats. If you don't know what word to type in, you can always look, if you go in the calculator. Come on, calculator. And you go to functions. you can either look in stats or distribution. These are going to contain the two things we're using currently. So under stats, right, you could find the mean, you got your quartiles, standard deviation for the population, standard deviation for the sample. So we have all that stuff in here. So if you're not sure what to type in, go into this list and it's kind of your cheat sheet. So if I want the standard deviation for the population, all I got to do is type that in, put my list in parentheses, and there we go. There's my standard deviation. So real simple if you're going to do that in Desmos. Let me know if there's any issues with that, of course. Let me go to the next one. So the reason we're talking about standard deviation is because when you get into normal distribution, which is what we're doing right now, and this is probably new to most people, I would think, normal distribution. You usually don't do this unless you take a statistics course. So when you get into normal distribution, things are distributed depending on the standard deviation. Okay, so as you look at what we call a bell curve, this is a bell curve, and this is the curve that represents a normal distribution function. And here's kind of how it works. Right here in the middle is the mean. So whatever this data value is the center of your normal distribution curve. All right, that's the mean. As you move to the right, you are adding standard deviations onto the mean. So if I took the mean plus 1 standard deviation, I would get that guy. If I added 2 standard deviations onto the mean, I would get that value right there, and then this would be 3 standard deviations. If you went the other way, you're subtracting standard deviations. So if I took the mean and subtracted 1 standard deviation, I get that point. This would be minus 2 standard deviations, and this would be minus 3. So you get 7 values across the x-axis. So you got the mean in the middle, and then you are moving out away from the mean with standard deviations. It is symmetric on both sides. So from here to the left is 50% of your data. From here to the right is another 50% of your data. As you get within certain standard deviations, there are certain percentages that are just accepted. I wanted to see if I had a graph on the next page. I do. So I don't have to fill it into this. There are certain percentages that are accepted if you're within 1 standard deviation or if you're within 2 standard deviations and so on. Now all this can be done in a calculator, and it's much more accurate in a calculator, but you should at least know what these guys are. So FYI, there's 2 different symbols for a mean. You've seen it in my calculator that I had the x with the line over it. That is commonly accepted as the mean. This Greek letter mu, mu, is also used for the mean. So that's what they're using on this. But same meaning, different symbol. So anyway, if you are within 1 standard deviation of the mean, left and right, you're looking at 68% of all of your data. If you are within 2 standard deviations of the mean, you got 95%, and within 3 standard deviations, you're looking at 99.7% of all of your data. So obviously, almost all of your data should be within 3 standard deviations of the mean if things are normally distributed. Guys, this is called normal distribution because it's basically like your standard of comparison. Okay, so pretend for a minute that you had someone come to our country from a different country, and you told them they got a C on the test. Well, if they don't use the same letter scale that we do, they'll have no idea if a C is good or bad, right? They need something to compare it to. So is a C good? I don't know. Well, if you told a student that most students in the class got a B, and the C was the next letter down, then that means they didn't do very well. But if most students in the class got a D, and you tell them that a C is higher than that, well, then that means they did pretty good compared to the rest of the class. So you need to have a basis of comparison in order for stuff to make sense. So that's what normal distribution is. It's the standard that you would compare your distribution to. Okay, so if things were normally distributed, which will probably never happen in a real life scenario, this is what you would compare it to, your data to see how it measures up. let me show you these three data values on a graph. So remember, you have the mean in the middle. So this is the mean right here on that line. So if I'm within 1 standard deviation of the mean, so that means from 1 standard deviation below it to 1 standard deviation above it, that area, that gray area, contains 68% of all of my data. It is symmetric, so that means 34 of that percent is right here, and the other 34 is right there. Okay, so if you're within 2 standard deviations of the mean, so from here to here, should contain 95% of all of your data. So again, it's symmetric, which means 47.5 is here and 47.5 is here. Now you could start breaking this down, because if this is 34 and the whole thing is 47.5, that means this little space is 13.5%. So you could start separating it out into little groups like that. But the third one is 99.7 is from here to here. Contains 99.7% of all your data, which means there is a little bit outside of that. All right, so there's a tiny little bit out here, there's a tiny little bit out here, but this is just a general rule. If we use a calculator, you're going to get numbers that are close to this, but a little more accurate if we calculate it. So take a look at this. So here's a better drawing than my drawing. All right, so draw a normal distribution curve with this data. So the average, the mean, scored by an NFL team in a game last year was 22 points. Standard deviation was 4. So what would that look like in terms of this diagram? So let me just do a complete layout of the diagram, and then I'll give you some questions that they might ask you. So we always put the mean in the middle, right? So they said the average was 22 points. The standard deviation was 4, which means from here, if I add 4, I get that guy, and I'm just going to keep adding 4s to get these values on the graph. And then if I subtract 4s from 22, we'll get these values. All right, so those are kind of the main data values. Now, using the percentages up above, remember, as we start breaking down these little categories, so if there's 68% of my data was from here to here, that means 68%, if this was accurate, it's probably not, but if it was accurate, then that means 68% of all the teams scored between 18 and 26 points. Remember, this is symmetric, which means 34% was here. The other 34% was right here. So, in other words, 34% of the teams scored between 18 and 22 points. That's kind of how we would interpret that. So, the rule from 2 standard deviations was 95%. So, from here, from 14 to 30, contains 95% of all the data. So, in other words, 95% of the teams scored between 14 and 30 points, according to this information. So if we separated that out, that means from here to here would be half of that 95, which is 47.5. Well, if that's 34, that leaves this as 13.5%. In the next lesson, we're going to learn how to do these in calculator. So I'm just showing you based on general rules for today. One more little piece. Remember, the whole thing from 10 to 34 was 99.7% of the data. Okay, so there's very tiny little bit outside of that. So in other words, potentially no teams scored fewer than 10 or more than 34. If it did happen, it was a very rare occurrence. Let me just do a little quick math on this. So 99.7 divided by 2 is 49.85. Sorry, it's getting a little dark in here. So that represents from 10 to 22, should be 49.85. So if I take away the two amounts that are already there, so minus 34 and minus 13.5, that leaves me with 2.35 for that little space, which I can't even fit in there, and right here. So what's left on the outside? That would leave you with a 0.15% to the far right of 34 and 0.15% to the left of 10. If we really broke all that down. So here's the kind of questions they're going to ask you. So they're either going to say, well, what's the probability that a team scores between 14 and 26 points next season? Well, just add up the percentages. So from 14 to 26, if I did 13.5 plus 34 plus 34, that would be my answer, right? That would be the probability or the percent that a team would score between 14 and 26 points. What if they said, what's the probability that a team scores more than 34 points? Well, there's a 0.15% chance that a team scores more than 34 points. Right? So those are the types of questions they ask, but obviously very, very simple once you have the diagram laid out, because they're going to give you numbers that you see right here. So if we didn't get numbers that are on that list, like what if I said, what's the probability that a team scores less than 20 points? Well, 20 is not on my list, and that's where the calculator comes into play. So that's what we're going to see next time, but this is going to do it for this part.